A recent South Australian scheme decided to put a Tesla Powerwall into some socially disadvantaged housing to help with the electricity bills. So how would that fare, and how does it compare to a system with energy storage and solar? Hi, I'm Billy from Greenwood Solutions. After watching this presentation, you'll understand the advantages or disadvantages of an energy storage only approach as compared to energy storage and solar from the perspective of negating a certain percentage of your electricity bills. Now, if you like what you see with these videos, hit that subscription button. Let's get stuck into it. A recent South Australian scheme looked at installing in socially disadvantaged housing a TESLA Powerwall 2 with no renewable energy component at all to help with the bills. So what kind of savings can be achieved with this particular strategy? We're going to look at the overall savings on these gifted systems and then look at what kind of payback period you'd get if purchasing a system and what are the other options available to spend your money on. Energy storage effectively should always be incorporated with a solar energy component unless it has been gifted, and even then it's negligible in regards to what benefits can actually accrue to the customer involved, because energy storage by itself purely relies on the discrepancy, the difference between the off-peak tariff and the peak tariff. In the scheme mentioned, the participants were each given a TESLA Powerwall 2. The total energy capacity was 14 kilowatt hours. The usable energy capacity was 13.5 kilowatt hours. Assumed max discharge power of 3.3 kilowatts with an ideal temperature of 25 degrees C. Yeah, perfect world, which really never happens in reality, but anyway. So how will this system save money? It's all based on the assumption that there is a peak tariff, an off-peak tariff period, and the difference between the two is considerable. So we'll look at a peak tariff of 7 a.m. to 10 p.m, 7 days a week. Look, usually there's an off-peak tariff on weekends, but in this situation, I haven't gone down that road. Now, the peak tariff is 25 cents per kilowatt hour. The off-peak tariff is from 10 p.m. to 7 a.m, 7 days a week, and the off-peak rate is 14 cents per kilowatt hour. Now, when energy is drawn from a battery, it has to be replaced, and this replacement process is not 100% efficient. Now, the data sheet on the TESLA Powerwall says a round trip efficiency of about 90% at the beginning of the life. I will assume 85% on the charge process, and I'll also assume the battery lasts its full warranty period of 10 years. We're going to assume that the home in question has an average daily load of 20 kilowatt hours a day. Let's say that the battery delivers 13.5 kilowatt hours a day, 365 days a year for 10 years. So the battery delivers 49,275 kilowatt hours over its entire life, and that's the discharge. The energy required to replace this energy is 49,275 divided by 0.85, so 85% charge efficiency, and this equals 57,970 kilowatt hours. So this equates to an extra 8,695 kilowatt hours from the grid, because remember, what comes out of the battery has to go back in, and there's an inefficiency in the charge process. Now, the battery delivers 13.5 kilowatt hours a day, so in the first year the battery saves $1,231. Now, I've done this with a spreadsheet, but it costs $811 to refill the battery via the grid at the off-peak rate. So the net benefit to the household is $420 in the first year. This equates to $1.15 a day, or 4.6 kilowatt hours a day at the peak rate of 25 cents per kilowatt hour. Now, what about over 10 years? Let's assume that the household continues to use the maximum for the TESLA Powerwall 2 of 13.5 kilowatt hours a day, and the peak and off-peak price increases 2% every year. So year one saving of $420, we've established that. Year two cumulative saving of $853. So that's the saving in the second year added to the first year, and year 10 cumulative savings of $4,626. So that sounds pretty good, considering the batteries are for free. But what if there's less of a difference between the peak and off-peak price? Now this is great if you don't have to pay for the system, and it is based on a fairly large discrepancy between peak and off-peak. For example, what if off-peak rate was 19 cents? Well, the year 1 saving would be $133. The year 2 cumulative saving will be $270, and the year 10 cumulative saving will be $1,461. So we're not looking so good now. If you had to pay for the system, what would the savings look like? Let's assume to supply and install, a company charges 15 grand for the TESLA Powerwall 2. How many years would it take to pay off? Again, we're going to assume 25 cents per kilowatt hour and 14 cents per kilowatt hour. So 25 for peak, 14 for off-peak. We're going to use all the 13.5 kilowatt hours available, and we're going to charge back up 85% efficiency. 27 years. Hang on, the product's warranted for 10 years. So 27 years to pay back based on those assumptions. Now, what if I invested that money in the bank instead? At the moment, interest rates are pretty low, so we'll assume I can access 1% interest compounded monthly. So we get a $15,000 investment for 27 years at 1% compounded monthly. So you can see that the investment value at the end of the term is $19,647.26. Total interest earned is $4,647. Now at 1.5%, the savings go up to $22,483. What if we incorporated renewable energy? So if we add a renewable energy component, solar, loads can be less reliant on the grid even more, and the solar can charge the batteries ready for the evening loads, and both the batteries and solar can work together during the day. We know we have a 20 kilowatt hour a day household load. Let's add 5 kilowatts of solar. We'll assume a daytime-nighttime load ratio of 60-40. Solar will produce on average 5 times 3.6, so 17 to 18 kilowatt hours a day. Now I'm assuming Melbourne. Obviously in the northern cities of Australia and other parts of the world, you're going to get more output on average per day. The total cost of the system, and I'm making assumptions, is $20,000 plus GST. Solar obviously only produces during the day. So during the day, 60% of total loads are consumed. This equates to 20 kilowatt hours times 0.6. So we're looking at 12 kilowatt hours can be addressed with the solar component. So the remaining 5 to 6 kilowatt hours can contribute to battery charging. So remember, you're producing about 17 to 18 a day on average. In reality, it is not that simple, as there are many factors that play a role. What would the financials be on solar only? We're assuming a 2% increase in electricity. We're also assuming the panel's output reduces 2% after the first year, and after that reduces 0.25% a year. Now you'd paid back within about 7 years. But now batteries and solar, let's make some assumptions. We know 60% of all loads are consumed during the day. So the solar can now send energy to the batteries, less export to the grid, and directly address loads during the day. Overnight, the batteries will contribute 8 kilowatt hours out of a possible max available of 13.5 kilowatt hours. Remember, that was what's available from the TESLA Powerwall. The question is, do we allow the grid to fully replenish the batteries or partially? The reality is, there is no perfect charge-discharge cycles. Batteries will contribute to loads in the morning and afternoon if solar isn't enough. Assumptions. Here goes. Loads are high in the morning, average at midday and slightly less in the afternoon. Batteries and solar will double team throughout the day to address the loads. Batteries at start of evening, no solar, are full and ready to go for the evening. There will be some export of solar to the grid. Batteries will be fully replenished overnight by grid and fill the 8 kilowatt hours used overnight. 90% of the solar will be used during the day, loads and battery charging. So you can see from this particular table that after 10 years, your payback is $19,679, and the total cost of the battery and solar system was $20,000. So this results in a payback of about 11 years. So we've got energy saved from the battery in column 2, energy spent on charging the battery from the grid in column 3, the net savings in column 4, the cumulative savings in column 5, the solar contribution savings in column 6, batteries and solar together in column 7, and batteries and solar cumulative in column 8. Conclusion: energy storage only system can negate a certain amount of energy from the grid, but this scenario relies on a difference between peak and off-peak tariffs. It's more viable to have a combination of solar and energy storage. There are many factors to consider when making assessments of the worth of energy storage. Thanks so much for watching our presentation on energy storage compared to energy storage and solar. I'm Veli from Greenwood Solutions. If you like what you see and you want us to make more of these videos, hit that subscription button. See you next time. You may have noticed this thing sitting in front of me. Any guitarists out there? Because you guys will know what this is. Big shout out to Eddie, our director.